We will now look at an algorithm that takes a set of functional dependencies and it computes from them a small representative set that implies all the original functional dependencies. And this small representative set is called a canonical set of functional dependencies. Let F be a set of functional dependencies. We now compute a canonical or minimal set of functional dependencies that is equivalent to F. And we will do so by transforming F step by step. The first step is to make all the right-hand sides singular. So if we have a functional dependency of the shape alpha, so alpha can be a set of attributes, alpha uniquely determines B1 up to Bm, then we replace this by m functional dependencies, alpha uniquely determines B1, alpha uniquely determines B2, up to alpha uniquely determines Bm. So after this step, all the right-hand sides just contain a single attribute. Next, we minimize the left-hand sides. So we look at all functional dependencies, alpha uniquely determines B, and at all attributes A in the left-hand side. Then we take the set alpha, the left-hand side, we remove A. So at this point we do not yet remove A from the left-hand side of the functional dependency, just from this set, and we compute the cover with respect to the unchanged functional dependencies F. And if this cover contains B, then this means in order to conclude that B is unique, we did not actually need all the attributes alpha. It was sufficient to take alpha without A. And that means that we can replace the original functional dependency, alpha uniquely determines B. We can replace this by the same functional dependency where now A is removed from the left-hand side. So again, first we look whether from the left-hand side without A we can still derive B, and if so, we can drop A from the left-hand side. And next, this is the final step, we remove all the implied functional dependencies. So we look at all of the dependencies alpha uniquely determines B, and then we check whether this functional dependencies is implied by the other functional dependencies. So how do we do this? We take the left-hand side and we compute the cover of the left-hand side, but now not with respect to F, but with respect to G, where G is all the functional dependencies other than A uniquely determines B. So we remove from F the functional dependency A uniquely determines B, and we call this set G, and then we check whether from the left-hand side, using only the other functional dependencies, we can still get to B, and if so, then it means that we actually didn't need this functional dependency, and we can drop it from F. And we repeat the steps 2 and 3 until nothing can be removed anymore, until no attributes can be removed anymore from the left, and until no more implied functional dependencies can be removed. So the order of the steps 2 and 3 is not really important. We can also first remove some implied functional dependencies, then minimize, then remove implied again. So we should just check that we repeat this step until nothing is possible anymore. So let's have a look at an example. We're going to apply the algorithm to compute a canonical set of functional dependencies to this set of functional dependencies. The first step is to make the right-hand sides singular. There's only one functional dependency with more than one attribute on the right, so we split this. We will split this functional dependency into two functional dependencies, A uniquely determines D and A uniquely determines E. This is the result of this split. All the other functional dependencies already have a single attribute on the right, so there's nothing to be done. The next step is that we minimize the left-hand sides. There's only one functional dependency with more than one attribute on the left, so this is the only one that we may potentially minimize. So first let's see whether we can drop the b. So we take the set of the left hand side without the b, so that we only have the c, and we compute the cover of c. What do we get if we start from c and we compute the cover? None of the functional dependencies is applicable, so we only get c. We do not get to d. So that means dropping b is not an option. We would no longer get d. Now let's try what happens if we would drop c. So we start from b and we compute the cover of b. From b we get c via this functional dependency. And then we have b and c, and then this functional dependency is applicable, and we get d. So that means we get d already from b alone. We don't need c to uniquely determine d. So we can drop c from the left-hand side of this functional dependency. So we get just b uniquely determines d. And the last step is we remove implied functional dependencies. So let's have a look what functional dependencies are implied here. For instance, we have a functional dependency a uniquely determines e, and we have functional dependency a uniquely determines d, and d uniquely determines e. If we take a uniquely determines d and d uniquely determines e together, then they imply a uniquely determines e. That means we can drop the functional dependency a uniquely determines e without losing any information. So this functional dependency is implied and we drop it. Now there's nothing anymore that can be removed, so we are done. And this is the set of canonical functional dependencies that is equivalent to our original set of functional dependencies. Let's look at a bit more complicated example. Now we are considering this set of functional dependencies and we want to compute a canonical set of functional dependencies that implies all these. The first step is again to make the right hand side singular. Now we have two functional dependencies, this one and this one, with more than one attribute on the right. So we split them. The result of the splitting is this set of functional dependencies. Now there are some functional dependencies that are obviously implied by others. For instance, the functional dependency ABC uniquely determines E is obviously implied by B uniquely determines E. We do not need A and C, already B uniquely determines E. So we can drop this functional dependency. Also B uniquely determines E can be dropped because it is implied by B uniquely determines C and C uniquely determines E. These two together imply B uniquely determines E. So this one can be dropped as well. And then we have one more functional dependency, CD uniquely determines D, which obviously can be dropped because it's trivial, so it's always implied. So dropping these three implied functional dependencies gives us this set of functional dependencies. Now we have to minimize the left-hand sides. So let's look at the first functional dependencies. What attributes from the left-hand side can we drop? So we have A, B, C on the left-hand side, and we wonder, can we drop one of them and still get to D? Now observe that the only way to get to D is by using ABC. There's no other way. This functional dependency gives us C, this gives us E, this gives us F. There's no other functional dependency that gives us D. So the only way to get to D is via ABC. Now, dropping A is not an option because there's no way to get A back. So then we can never apply this functional dependency. Dropping B is not an option because there's also no way to obtain B It's not in any right-hand side of any functional dependency. Now, the last option is dropping C. So let's see if we take the set AB. From AB, can we still get to D? We have AB, then from B we get C, so then we have ABC. Then we can apply this functional dependency and we get D. So indeed, C can be dropped from this functional dependency. Here we have C and D uniquely determines F. The question is, can we drop one of them? Can we drop C or can we drop D? Let's start with considering C. So we have only D. The question is, can we get from D to F? If we have only D, then none of these functional dependencies is applicable, so we get only D, we don't get F. Now let's assume that we want to drop D, then we start from C. What do we get if we have C? Then we get E, and then we're also stuck. We don't get anything anymore, we just get C and E, we don't get to F. So from this left-hand side we cannot drop anything. But from this functional dependency we can drop C and still get to D. So dropping C gives us this set of functional dependencies. Now there's nothing that we can do anymore. There's no more implied dependency to remove. There's no more left-hand side to minimize. So this is the final result. This is our set of canonical functional dependencies. Let's practice the computation of canonical sets of functional dependencies in the online system. Here we are asked to compute the canonical set of functional dependencies for this set of functional dependencies. So I will start by copying this set of functional dependencies. For better readability, I will replace the arrow. Okay, the first step is to make the right-hand side singular. So we split functional dependencies that have more than one attribute on the right. Okay, so we've split all the functional dependencies. Now let's order them a bit nicer, that we have some overview. Okay, now let's start cleaning up by removing some implied functional dependencies. Let's see, just a quick check. We have AD uniquely determines B and AD uniquely determines C, but from B we can already conclude that C is uniquely determined. So we don't need AD uniquely determines C. It is implied by AD uniquely determines B and B uniquely determines C. What else do we have? We have DE uniquely determines A and DE uniquely determines B, but we already know A uniquely determines B, so we don't need DE uniquely determines B. It follows from DE uniquely determines A and A uniquely determines B. Likewise, we don't need DE uniquely determines C, because we have DE uniquely determines A determines B, and B determines C. Okay. Can we remove something else? I think we can also remove AD uniquely determines E. because if we have, so AD uniquely determines E, let's have a check. So if we want to formally check whether a function dependency is implied, we take the left hand side and we compute the cover, but now we compute the cover not taking this function dependency into account. So I comment this function dependency out for the moment. So we compute the cover without this functional dependency. So this is ignored. Okay. So what do we get? If we take AD, then we definitely get from A we get B, from B we get C, and from AC we get also E. So E is still reachable even without using this functional dependency. So this functional dependency is implied. So we are allowed to remove it. We can get from AD to E without using this functional dependency. Okay, so we can remove this. The functional dependency AD uniquely determines B is obviously implied by A uniquely determines B. We don't even need the D. So we can also remove this one. Now I don't see any more. Oh yeah, one more. AC uniquely determines B is of course implied by A uniquely determines B. We don't need the C, the B is immediately uniquely determined by A. Okay. Okay, that looks good. Now we have removed implied function dependencies. Now we need to check whether we can minimize left-hand sides. Okay, we have two function dependencies with two attributes on the left. So let's look whether we can remove something. If we would remove C here, we would only have A. What's the cover of A? We get A. Do we get something else? We get B. We get also C. And since we have C, we can apply the functional dependency AC uniquely determines E, so we get E. So that means we don't need C here. Also without the C, E is reachable. So we are allowed to drop the C. Now let's have a look whether we can remove something from this function dependency. Let's compute the cover of D. So assume we would remove E. What would we get? The cover of D just gives us D, nothing else applicable. So we cannot reach A from D alone. Now let's compute the cover of E. What do we get? From E also we don't get anything. We can also not reach A. So neither D nor E can be removed without losing the ability to reach A. Okay. Very nice. So our left hand sides are minimal. We need a final check whether we have implied functional dependencies. If we start with A and we compute the cover, now ignoring this functional dependency, what do we get? We get A, we get E. We don't get anything else. So we cannot get to B anymore. So we cannot remove this functional dependency. It's not implied. For AE, now we take the cover of A, but we ignore this function dependency. What do we get? We get A, B, we get C, we get D. But we don't get E anymore. So there's no way to get to E. So this function dependency is also not implied. What about BC? Actually, it's obvious that BC is not implied because this is the only function dependency that allows us to reach C on the right hand side. So we need it. Likewise, BD is not implied. It's the only function dependency that allows us to get to D. And likewise, DE uniquely determines A is not implied because it's the only function dependency that allows us to uniquely determine A. Okay, so this is a canonical set of function dependencies. Let's check our solution. yes, our solution is correct.